Hello, good morning to all of you. I hope all of you are doing well. So in today's class, we're going to discuss pin configuration of 8085 microprocessor. Now, 8085 microprocessor has a net 40 pins. And associated with 40 pins, there are 40 signals. Okay, so we'll go through the signals in sequence. So X1 across pin 1, so X2 2, reset out 3, SOD 4, SID 5, trap 6, RST 7.57, RST 6.58, RST 5.59, INTR 10, INTA 11, AD0 12, AD1 13, AD2 14, AD3 15, AD4 16, AD5 17, AD6 18, AD7 19, ground that's 20, and A8 21, A9 22, A10 23, A11 24, A12 25, A13 26, A14 27, A15 28, S0 29, ALE 30, write 31, read 32, S1 34, 33, IO oblique M bar 34, ready 35, reset in 36, clock out 37, HLDA 38, HOLD 39, and power VCC 40. So these are the 40 signals that are sent through the 40 pins of the 8085 microprocessor. Now, there are a few important properties that I want you to go through before moving on with the pin description of 8085 microprocessor. That is, 8085 operates on single plus 5 volt. It has 4 vectored interrupt, out of which one is a non-maskable interrupt. It has a serial input and serial output port. The direct addressable capability of 8085 microprocessor is 64 kilobyte. Now, 8085 uses multiplex address data line in order to limit the number of pins. So we have a multiplex address data line AD0 to AD7. Now let us move on with the pin description of 8085 microprocessor. Now the following are the descriptions of the pins. So we have A8 to A15. Now A8 to A15 is used in order to host the most significant 8-bit of the address or 8-bit of the IO address. So A8 to A15 is used to host or hold the most significant 8-bit of the address or 8-bit of the IO address. Likewise, AD0 to AD7. Now, AA to A15 is a unidirectional line. Likewise, AD0 to AD7, it is address data multiplex lines. Now, AD0 to AD7 is used in order to hold least significant 8-bit of the address in the first clock cycle of a machine state. Again, I'll repeat it. AD0 to AD7 is used to hold least significant 8-bit of the address in the first clock cycle of the machine state or 8-bit of the IO address. Now, these are bidirectional in nature. And subsequently, in the second and the third clock cycle of a machine state, it is used to hold data. So, in the first clock cycle of a machine state, it acts as a unidirectional line, and in second and the third clock cycle of a machine state, it acts as a bidirectional line because data can be communicated to and from the microprocessor, right? Now, ALE is an active high signal. It occurs in the first clock cycle of a machine state and it enables AD0 to AD7 operate as A0 to A7. Right? Again, I'll repeat it. ALE occurs is active high signal. It occurs in the first clock cycle of a machine state and it enables AD0 to AD7 operate as A0 to A7. So with the aid of ALE, AD0 to AD7 operates as A0 to A7, that is address lines. Now S0 and S1, these are active high signals. These signals are used in order to represent the status of the data bus. Okay, it is used in order to represent status of the data bus. So the combination represents various operations. So S1 and S0, if both S1 and S0 are 0, it represents halt. If S1 is 0 and S0 is 1, then it's write. If it is 1 and 0, it is read. And when it's 1 and 1, it represents fetch. So 0, 0 represents halt, 0, 1 represents write, 1, 0 represents read, and 1, 1 represents fetch. So it is capable of representing the data bus status and what kind of operation we are performing. So whether we are performing read operation or write operation or fetch operation. So correspondingly, what we need to do is we need to look into the values of S1 and S0, right? Now the next signal that we're going to discuss is read. So read is active low signal. It's a barred signal. Read indicates that the selected memory address or IO device is to be read and the data bus is available for data transfer. Okay. Again, I'll repeat it. Read is an active low signal that indicates that selected memory address or IO device is to be read and the data bus is ready for data transfer. Okay. Now likewise, write is an active low signal that indicates that data on the data bus is to be written onto a specified memory location or IO location. Okay. Again, I'll repeat it. Write is an active low signal. Write is an active low signal that indicates that data on the data bus is to be written onto selected memory location or IO location. Right? So this is the difference between a read and write. Now ready. Ready is an active high signal which indicates that the memory or peripheral device is ready to receive or send data. Again, I'll repeat it. Ready is an active high signal that indicates that the peripheral device or memory device is ready to send or receive data. And if ready is high, so ready has to be high during read or write cycle, because only then what we can do is we can perform read or write operation. Now if ready is low, then CPU will wait for ready to be high or ready to go high before completing the read and write cycle. So that's the utility of the ready. So ready indicates that memory or my peripheral device is ready to send or receive data. So it's active high signal. Now hold. Now hold is an active high signal that indicates that another master is requesting for the use of the system buses. Okay, again I'll repeat it. Hold is an active high signal which indicates that there is another master requesting for the use of address and data buses. Right. So whenever the microprocessor receives a hold signal or hold request, what it will do is it will relinquish the use of the buses as soon as the current machine cycle is completed. So whenever a CPU whenever a CPU receives a hold request, then it will relinquish the use of the buses as soon as the current machine cycle gets over, right? But the internal processing continues. The internal processing of the microprocessor continues only what it will do is it will relinquish the use of the various system buses. Now the processor will regain the control over the buses after hold is removed. Okay, so once the external master relinquishes the buses, then what we can do is we can make the microprocessor use the buses. So the processor can regain the buses only after the hold is removed. Now hold acknowledgement, it's an active high signal, right? Again, hold acknowledgement is active high signal. So hold acknowledgement indicates that the CPU has received the hold request and then it will relinquish the bus in the next clock cycle. This is very much important because whenever there is an external request for the use of the buses, the microprocessor has to acknowledge the request, right, through hold acknowledgement. So hold acknowledgement indicates that the CPU has received the hold request and then it will relinquish the bus in the next clock cycle. Hold acknowledgement goes low after the hold request is removed. Now INTR is the interrupt request. Okay, so it's used as general purpose interrupt. So it is so INTR is an interrupt request. So it is a general purpose interrupt, and it's sampled only during the next to the last clock cycle of the instruction. Because what we need to do is we need to know whether there is an interrupt request or not. So every time what we do is we sample the interrupt request in the next to last clock cycle of the instruction. It's called as next to last. That is the second last. Okay. clock cycle of the instruction. So if it is active, then the program counter will be inhibited from incrementing, because now what we need to do is we need to stop the current execution, and we need to transfer the control to the subroutine. So then after that, so after the incrementation of the program counter is inhibited, INTA, interrupt acknowledgement, will be issued, right? So then what we'll try to do is we'll try to jump to the interrupt service routine and execute the interrupt service routine, and again come back and then relinquish and continue the execution in the in the calling module. So interrupt request is INTR, interrupt request, a general purpose interrupt. So it is sampled only during the second next to the last clock cycle of the instruction. So if it is found active, then the program counter implementation is inhibited, and interrupt acknowledgement is issued. And whenever once the interrupt acknowledgement issued, what we can do is we can transfer the control to the interrupt service routine, get the interrupt service routine executed, and then again return back to the calling function. Now, interrupt acknowledgement, as we have said, that whenever interrupt request is being received, okay, so what we need to do is we need to acknowledge it. So interrupt acknowledgement is used to acknowledge the interrupt. So when microprocessor receives interrupt signal, it sends an acknowledgement, that is INTA, to the peripheral which is requesting for its service. Now let us try to understand what is vectored and non-vectored interrupt. So vectored interrupts are interrupts with which a vector address is associated. Okay, again I'll repeat it. Vectored interrupts are interrupts with which vector address is associated. So, for an example, trap. Trap is a vectored interrupt where the vector address is 24H. RST 5.5 is a vectored interrupt where the vector address is 2CH. RST 6.5 is a vectored interrupt where the vector address is 34H. RST 7.5 is a vectored interrupt where the vector address is 3CH. So these are all vectored interrupts with which what we have is we have associated vector address, or the location where the control transfer is to take place. Now, for software software interrupt, vector address is estimated or calculated using the formula 8 into the vector type. So we have 8 software interrupts that we have, RST0 to RST7. Now what we do is we try to calculate the vector address by multiplying the interrupt number with 8. So 0 into 8 is 0, 1 into 8 is 8, 2 into 8 is 16, 3 into 8 is 24, 4 into 8 is 32, so this is 32 in hex, right? 5 into 8 is 40, and then 6 into 8 is 48, and 7 into 8 is 56. So this is the way how we estimate the vector address of the software interrupts. So these are hexadecimal representation of the vector address. So this is 0, this is 8, this is 16, this is 24, this is 32, then this is 40, this is 48, this is 56, right? Non-vectored interrupts are interrupts with which no vector address is associated, and what we need to do is we need to provide the vector address, right? Okay, or the interrupt address. So INTR, as we have discussed, is the only non-vectored interrupt 8085 microprocessor has. So whenever INTR request is sent, what we need to do is we need to also specify the address of the interrupt service routine. So INTR is a non-vectored interrupt. Okay. Now let us try to distinguish between maskable and non-maskable interrupt. So maskable interrupts are interrupts which can be disabled or ignored by the microprocessor, right? Again, it can be edge triggered or it can be either label triggered. So it can be edge triggered interrupt or label triggered interrupt. So maskable interrupts are interrupts that can be disabled or ignored by the microprocessor. Whereas non-maskable interrupt is an interrupt that cannot be ignored or disabled by the microprocessor. So, for an example, INTR, RST 7.5, 6.5, and 5.5. These are maskable interrupts. Okay, INTR, RST 7.5, 6.5, and 5.5. These are maskable interrupts, whereas trap is a non-maskable interrupt. So that is the way how we distinguish between maskable and non-maskable interrupts. So maskable interrupts are interrupts that can be disabled or ignored by the microprocessor. It can be edge triggered or label triggered. triggered. INTR, RST 7.5, RST 6.5, and RST 5.5. These are maskable interrupts. Whereas non-maskable interrupts are interrupts that cannot be disabled or ignored by the microprocessor. So trap is an example of a typical example of a non-maskable interrupt. Now reset in. Now reset in again is a active low signal. So whenever this particular signal goes high, is high. So the high basically means whenever it becomes zero, the program counter is set to zero. So this is very much important. So whenever reset in becomes high or it becomes zero, then the program counter is set to zero. The bus are tri-stated and the microprocessor unit is reset. Now, this is what happens whenever reset in signal becomes high. So the program counter is set to zero, the buses are tri-stated, and the microprocessor unit is reset. Likewise, reset out. This signal indicates that the microprocessor unit is being reset. The signal can be used to reset other devices. So reset out is an active high signal that indicates that the microprocessor is being reset, and the signal can be used to reset other devices that are there. Now X1 and X2. So X1 and X2, it's a crystal or RC network, and it's connected to the two pins X1 and X2. The frequency is internally divided by 2. Therefore, the operating frequency is internally divided by 2. So to operate a system at 3 megahertz, the crystal should have frequency of 6 megahertz. So as the frequency is internally divided by 2, therefore, if a device is to operate at 3 megahertz, the crystal should generate a frequency or should have a frequency of 6 megahertz. So X1 and X2. So these are used for frequency as a medium for generating frequency. Okay, right? Now IO oblique M bar. So IO oblique M bar, so it indicates IO on or IO operation or memory operation. So if it is 1, it represents IO operation, and if it is 0, it represents memory operation. So whenever you perform read or write, what we do is we'll correspondingly have the necessary values for IO oblique M bar. IO oblique M bar. So if you are reading from IO devices, so it will be set to 1. If you're reading from memory device, it will be set to 0. Likewise, if you're reading from yes, so if you're writing into IO devices, IO will be set to 1. This signal will be set to 1, and if you're writing to memory, so it will be set to 0. So IO oblique M bar is used to distinguish between whether it's a IO operation or a memory operation. So SID, SOD. So SID is active high signal. The data on the line is loaded into the accumulator bit 7 wherever a RIM instruction is to be executed. So we'll come to SID and SOD whenever we'll be discussing the RIM and RIM and SIM instructions. So for now, just remember it is serial input data and serial output data. Both are active high signal. Right. So then we have VCC. So it requires plus 5 volt. And we have VSS, we have ground reference. So these are the descriptions of the various pins that 8085 microprocessor has. Okay, so we have discussed in today's class, we've discussed that the 8085 has 40 pins. Across the 40 pins, we have signals being communicated to and from the microprocessor. We have also come across the properties of 8085 microprocessor, that it requires plus 5 volt. It has 4 vectored interrupts. Okay, it has serial input and output port. Then direct addressable capability of 8085 64 kilobyte, and it uses multiplex address data lines. Okay. So then we went through the pin description of 8085. We discussed the role of A to A15, AD0 to AD7. Then we moved on to ALE, then the significance of S0 and S1. Then read and write, okay, and then ready, then hold and hold acknowledgement, and then interrupt request, interrupt acknowledgement. We discussed what is vectored and non-vectored interrupts, and we discussed the various vectored and the non-vectored interrupts that are there. We tried to learn about how to generate the vector address for software interrupts. That is by multiplying the interrupt number with 8. We also came across to know that INTR is the only non-vectored interrupt 8085 has. We discussed the maskable and non-maskable interrupt, and we went through the various maskable and non-maskable interrupt. we discussed the significance of reset in and reset out pin, then X1 and X2 for frequency, then IO significance of IO oblique M bar. We also briefly discussed SID and SOD. We'll be elaborating this on this whenever we'll be discussing the RIM and the SIM instruction. Okay, then we came across the supply supply required for 8085 microprocessor. Likewise, VSS ground. So thank you for listening to me. Okay, so thank you very much.